Hey guys, welcome back. Let us now do some examples. Here's the first one. We want to evaluate the triple integral of z over the solid E, which is the tetrahedron bounded by the following four planes. So first of all, let us visualize the tetrahedron. Well, this is the solid given by the blue region here in the figure. Notice the solid is bounded on the left hand side by the xz plane, whose equation is y equals 0. At the back, we have the plane x equals 0, which is the yz plane bounding the solid. And the solid is bounded below by the xy plane, whose equation is z equals 0. And also, the plane z equals 1 minus x minus y is bounding the solid from the top. Now, there are various ways we can visualize the solid, either as type 1 or type 2 or type 3 regions. And over here, I want to view this as a type 1 region. In other words, I want to view this object from the positive z-axis. So imagine putting our eyes here in the positive z-axis, then the shadow of the solid will be the projection of the solid, and it happens to be the triangular region on the xy plane bounded by the coordinate axis together with this straight line here. Do you see that? Now, a better picture of this triangular region is given below by this orange region. Now, where do we get the equation y equals y minus x, which is this straight line here bounding the triangle or triangular region? Well, this straight line comes from the intersection of the plane z equals 1 minus x minus y and the xy plane. So if we combine these two equations by getting rid of z, we'll have 1 minus x minus y equals 0, which is precisely this straight line here, okay, bounding the region D. Anyway, let us now describe this type 1 region. Well, the region is a set of points such that the xy comes from the projection D. Let us worry about this description for D later on. Let us now focus on the variable z. You see, the variable z is bounded below by the bottom surface and above by the top surface. If we look at the figure, the bottom surface bounding the solid is the xy plane, whose equation is z equals 0. So that's why we have the lower bound here given by z equals 0. And of course, the upper bound comes from the plane z equals 1 minus x minus y. That is the top surface bounding this solid. Right, next let us look at the description of the region D. Well, here we're going to regard D as a type 1 region. In other words, we are thinking of this being a region bounded by two vertical lines. So the first one here on the left is given by x equals 0, and another vertical line on the right bounding the region is given by x equals 1. So the range for x is between 0 and 1. Furthermore, for every such x between 0 and 1, let's say we have a point x here, then the y will start from the x-axis, going vertically, following this arrow, until it reaches the upper curve. So the lower curve, which is the x-axis, is given by the equation y equals 0. And the upper curve is given by the equation y equals y minus x. And we've got to express these two curves as function of x. So the lower bound for y is 0, and the upper bound for y is 1 minus x. You follow me? And now we are ready to compute the triple integral. So we're going to convert this triple integral into a double integral over the projection, followed by a single integral with respect to the z-axis. Alright, so this is what we have: a double integral over the projection, followed by a single integral with respect to z from the lower bound, z equals 0, as given just now in the description, to the upper bound given by 1 minus x minus y. The integrand remains the same. Alright, next we're going to expand the double integral. Since we have described this as a type 1 region, so the order we're going to use for this double integral will be the order dy dx. You see, we're going to place x outside because this is bounded by two constants in our description. Do you see that? Yeah, over here. And that's why we're going to place x at the most outer integral. The middle one will be the variable y from 0 to 1 minus x, as given just now in the description as well. So now we have, so the rest is just about calculating these iterated integrals, starting from the most inner one. So let's try to evaluate the inner integral with respect to z. Doing that, we'll get the resulting functions in terms of x and y. And next, we just have to evaluate this iterated integral dy in the order dy dx. And after some simplifications, we arrive at the final answer, which is 1 over 24. You follow me? Alright, let us move on to the next question. Here, we want to evaluate the triple integral of the function square root of x squared plus z squared over the solid E, which is the solid bounded by the following paraboloid and the plane y equals 4. Right, let me begin by sketching the surfaces bounding the solid. Let me start with the paraboloid y equals x squared plus z squared. Well, this is just an elliptic paraboloid opening up towards the positive y-axis. So this is a bowl-looking surface opening up towards the positive y-axis. Alright. Now the plane y equals 4 is just the vertical plane passing through the point 0, 4, 0 on the y-axis. So imagine 4 is somewhere here on the y-axis. Then we have this vertical plane bounding the solid. Alright. Here's a better picture of the solid E. And I'm going to view this as a type 3 region. In other words, I'm going to view this object from the positive y-axis. And imagine there were rays of light going towards the solid E from the positive y-axis. Then the shadow that we see on the xz plane will be the projection of this solid E. Okay? Now, you see the boundary of the shadow is precisely this intersection curve of the vertical plane y equals 4 and the elliptic paraboloid, right? Because if we were to extend these dotted lines towards the xz plane, then the shadow will be bounded by this circle. By combining these two equations, the radius of the circle is equal to 2, because this is the circle x squared plus z squared equals 4 on the xz plane. Do you follow me? So the projection is not the circle, but the region bounded by the circle. So let us call this the projection D. In fact, this is a disk of radius 2 centered at the origin on the xz plane. Let us worry about the region D later on. As a type 3 region, we need to determine the surface on the left hand side as well as the surface on the right hand side bounding the solid E. Well, to do this, we pick a point, let's say with coordinates x, z on the projection, and look for the horizontal arrows parallel to the y-axis starting from the left hand surface to the right hand surface. Well, it seems we have to start on the surface here and go all the way horizontally parallel to the positive, well, in the direction of y-axis until we reach the vertical plane y equals 4. Do you see that? In fact, this is true for any points we pick in the projection. So let's say we have another point here, then the horizontal arrow that we're going to use to cover the region will start from this point on the surface, in fact the surface on the elliptic paraboloid, and move horizontally parallel to the y-axis until we reach the vertical plane y equals 4. So it seems the left hand surface is the elliptic paraboloid and the right surface bounding the region is the vertical plane. Well, this is important because that's how we're going to describe our solid E. So let me write down the description of the solid E on the next page. Well, recall, as a type 3 region, E consists of points x, y, z such that xz comes from the projection D followed by the range for the variable y. And in general, y is bounded below by the left hand surface, which is given in terms of x and z. So let's say this is some function u1 of x and z, and likewise the upper bound is also some function u2 of x and z. Anyway, in our case, we have identified the left hand surface. So this lower bound here will be replaced by the elliptic paraboloid, which is given by y equals x squared plus z squared. So that would be our lower bound for y, and the right hand surface is the vertical plane y equals 4. So it's going to be the constant 4 for the upper bound. Next, we're going to describe the region D. Well, the region D turns out to be a polar rectangle. So for easier calculations later on, we're going to describe this region D in terms of the polar coordinates. Well, that's easy because both the polar coordinates are bounded by constant. Namely, D can be written as the set of points such that the polar coordinate r is bounded between 0 and 2, whereas the angle theta takes on the interval from 0 to 2 pi. Alright, we are now ready to calculate the triple integral. So as a type 3 region, we can convert this triple integral over E into a double integral over the projection, followed by the single integral with respect to the variable y, which is bounded below by the left hand surface, which is y equals x squared plus z squared, and is bounded above by the constant y equals 4, which is the right hand surface. Anyway, the integrand is constant as far as the most inner integral with respect to y is concerned. So by fundamental theorem of calculus, the antiderivative is the square root of x squared plus z squared times y. And now evaluate this antiderivative at the endpoints. We are going to get the following function in terms of x and z. So we arrive at the following double integral of some functions in terms of x and z over the projection D. And next we're going to convert this double integral into polar coordinates. Well, in doing so, we're going to replace dA by r dr d theta. Also, we're going to replace the integrand by its corresponding expressions in terms of the polar coordinates. But remember, we are doing polar coordinates on the xz plane, not on the usual xy plane. So in this plane, we have the following relations between the polar coordinates and the underlying variables. Namely, we have x being equal to r cosine theta, z being equal to r sine theta, and x squared plus z squared is equal r squared. In other words, the variable z plays the role of the variable y in the usual polar coordinates. Okay? Anyway, we're going to replace x squared plus z squared by r squared. So we're going to get r squared square root. Remember, in general, x squared square root is the absolute value of x. But in our case, the square root of r squared is absolute value of r. But then, r can never be negative. You see, r is the distance from the origins. So we can just ignore the absolute value sign. And hence, we have this, this term r here that comes from the square root term. And also 4 minus x squared minus z squared will be replaced by 4 minus r squared. The order we use for the iterated integrals doesn't really matter because both r and theta are bounded by constants. So here I've placed theta in the most outer integral, where it is bounded between 0 and 2 pi, whereas the variable r is bounded between 0 and 2 based on our description of the polar region D. Okay? And the rest are just some calculations of these iterated integrals. So after some simplifications, we arrive at the following real number. And that is the answer for the triple integral. Okay guys, that's all for now. See you next time.